Good day. I'm going to take you through the final counter, which will be the desynchronous counter. Once more, just going to state the steps and then go through them in detail. The first step being develop the state diagram, second being to develop the present state next state transition table, the third being to simplify the expressions, and finally to implement the circuit. So as we can see on the screen, the first step being the state diagram, just like the JK counter which we created, is only going to be 2 bits, thus we're only going to use 2 flip-flops. So once again, here you can see the bits in the order which we want them to be outputted. So again, 0 0 0 1 1 0 1 1 back to 0 0. All right, go on to step 2, the present state next state transition table. Once more, we have the present state an, bn, and the next states en plus 1 and bn plus 1. All right, and we have the inputs d and db. Again, we need the excitation table to fill in these inputs. And again, the first one is done for you, and I'll take you through how it is once more. So again, we use what the present state is and the next state to we use that to determine what the output, what the input should be. So we look in the excitation table. Again, we have 0 here, 0 here. So if present state is 0 and the next state is also 0, then the input needs to be 0. Again, that's what we have here, 0. And for B, if the present state is 0, next state is 1. Here, 0 and 1, the input needs to be a 1, and that is what we have here. Again, we're going to take a short break to fill in this table. It's one of the shortest tables you're gonna have to fill. All right, so this should be the table the inputs which you should have filled in. If not, please correct it, because we need them for the simplification of the input expressions. Again, we'll be using K-maps, but you are free to use Boolean algebra if you'd like. So for the first input, dA, we look at an, bn, and we see 0 0 will be 0 here, 0 1 will be 1 here, 1 0 will be 1 here, and 1 1 will be 0 here. For the second input, db, we have at 0 0 it will be 1 here, 0 1 it'll be 0 here, 1 0 it'll be 1 here, and 1 1 it will be 0 here. And that is it, just 2 K-maps, that's all that we need. And again, if we group the second one, we see that it will be not B. That's what this expression is, it's not B. So if B is 0, the output is 0, then that means you need 1 in the input for you to change, basically. And for this one, what this expression states is that the input is equal to A exclusively or B. This is what this expression says. Again, we will now use these simplified expressions to implement the circuit in Logisim. Alright, now as you can see, this should be the setup in your tutorial. So we are going to again use the logic from the simplified input expressions to connect the circuit together. Once again, you need to note that gates will be needed to connect this circuit. So we're going to start with the the second B flip-flop. So in the second flip-flop, again, it shows here that it is equal to naught of the output. So since the output here is 0, as can be seen, that means the input has to be 1. Alright, so to do this, we are going to first connect a NOT gate right here. Gonna just flip this to the west, connect this, and then connect this here. Fantastic. All right, and that is it for this one. Now we'll go to the first flip-flop. Again, what does it say? It says that the input is equal to A exclusively or B. So again, we need to take a gate. This time we are using an XOR since it will be exclusively OR. And let me place this a little high. All right, let's flip this to the west side and get 2 puts. Great. And once again, we are going to connect this here to A, and then we are going to connect this here to B, and then we are going to connect this to here. It should also be noted that, as you can see, there is a second output, the complement for the flip-flop. Now this could also have been connected to the input because it will be the same logic. This is not Q, and that is exactly what we want in here, not Q. However, I just use this NOT gate. So we basically put the circuit together. This is how it's supposed to look. And once again, let me go to the state diagram so that you can see exactly how it is when we simulate it. Once again, we see that it starts at 0, 0, enable ticks. Now it is at 0, 1, 1, 0, 1, 1, and back to 0, 0. And that is it. That is your desynchronous counter.